Hi everyone. My name's Adam. I'm here to talk about a open source modular wearable system that we've come up with in our project. If you're wondering why I'm walking up and down, it's because I've got a hamstring injury and I'm in excruciating pain. So I've taken the maximum amount of painkillers I'm allowed, so I'm just going to walk up and down to stop me hurting myself. So it might be a bit distracting, but that's why. So just bear with me. Okay, quick agenda. So very, very quick background to me and the project, because nobody wants to listen to me give you 10,000 words about what I've been doing. Talk about why yet another wearable platform, because surely we have enough by now, right? Talk about the use cases and the design of it, and why I think it's interesting. And then how to get hold and soon get hold of one, and then a Q&A afterwards. Is anybody in here that's played around with like open source wearables before? So there's literally a project called Open Source Wearables. Yep, excellent. Cool. Yeah, it's good. They are quite difficult to get into, as we'll discover. So, quick speaker and project introduction, world's worst photo. It's the only vaguely decent one I use. So I used to be at Pivotal VMware. Woohoo! For the people over there, Pivots, ex-Pivots. I'm now founder of Bilby Software, which is my own software company. I was also the founder of Linux of the Herald project. So I was the lead architect for the UK COVID-19 app, and I'm working with people like Terence over there during March to June 2020. Don't hold it against me. But once I finished that and went to bed for like a month to get over it, I then created an open source project, which is the Herald project. So that is what I'm here to talk about today, not Bilby Software, not stuff I'm doing at Oxford with my degree, but purely about that. I am a recovering software engineer. I realise there's lots of hardware people in the room. I'm getting there, okay. The Herald project, like I say, we founded it in summer of 2020. The idea being what we noticed rather quickly during the COVID-19 project was that the reliability of certain operating system vendors' Bluetooth stack was poor. And that's all I'm going to say on that subject. But it wasn't great. So I was like, well, whether it's for digital contact tracing or just transferring files from an iOS phone to an Android phone, let's try and make Bluetooth reliable. And whilst we're doing that, keep in mind on what we could use it for in the future. So, you know, obviously the proximity needs for a digital contact tracing application, and also maybe a completely decentralized digital contact tracing application that you don't need a central server for privacy reasons. So we're keeping an eye on that. So the Herald library, although we started with Bluetooth, it's not tied to Bluetooth. You can use other protocols, other transports. And it's not just mobile phones. We then moved on to a wearable, because one of the things we realized by talking to the UN Development Programme was that there's very many countries in the world that don't have $1,200 smartphones in everyone's pocket. There's quite a few of them. Obviously, for certain digital contact tracing layers that only supported $1,200 smartphones, that was a problem. So we worked on creating a low-cost wearable, which was the V1 Herald wearable, which we'll talk about in a moment. That's the website if you want to go and have a look. This is the V1 wearable. It wasn't that big, okay? That was 11 mil wide and about, if I remember rightly, 35 millimeters long. Very, very small. Underneath the fantastically designed NFC antenna is a fan-style chip, which has a Nordic semiconductor NRF 52833, for those who are very interested. That connector also, you'll see the non-connected band, the idea of that being it bends around the battery underneath that layer and plugs into a daughter board, which could have body monitoring sensors on. So, for example, COVID-19, one of the things we wanted to do and never quite got around to doing was look at blood oxygenation, because if somebody's blood oxygenation is kind of normal during an average day, and the next week it was down at 92%, which is at the point where you need to get to the hospital, we'd probably want to tell somebody about that, like the person who it's on, right? So that's one of the things we wanted to do. So we wanted to make sure that we had a pluggable secondary board. And this is where a lot of the next ideas came from. So we did that device, which just does Bluetooth storage and different frequencies of light to detect whether you're indoors or outdoors. So that was another big indicator as to the risk. So that was the first design. But that was really designed just for digital contact tracing or for COVID-19. What we've been asked and have conversations about since then is a wider range of things around personal health, personal fitness. So we were thinking, this is a bit limited because we've only got one daughter board and one form factor. So is there any way we can design something that's generic that different people could use? And that's where the V2 program came up from. So this is why we created it. So wide-ranging statement at the start. So I had a chat to quite a few open source projects on wearables, as well as medical researchers, and asked them what they were doing with wearables generally. And I found out that there was lots they wanted to do, but they were hamstrung by a few things. So the Open Smartwatch project, which you may know about, I had 2 watch designs, which I bought myself because it was a fantastic project, so I bought those myself to have a look at. But the problem was that when the designer wanted to change the screen, or they wanted to change the chip to like the next generation with a bit more memory, a bit more processing power, they had to redesign the whole thing from scratch. And this was a theme which I spotted throughout a whole host of projects. And then on the flip side of that, for the people who aren't computer scientists with hardware knowledge, but wanted to do medical research and say, hey, there's this fantastic new blood oxygenation sensor or heart rate monitoring sensor that I want to test out, if they just wanted to do that relatively simple thing, all of a sudden they had to design an entire smartwatch in order just to do that one thing, which when they're medical science students and not computer scientists doing an MPhil or DPhil, so a master's or a PhD project, that's a big ask because you don't get any credit for designing those things. You only get credit for the research you do. So you could do all this work and not have any credit. You write software, doesn't count towards your MPhil or your DPhil, right? Not that I've got a bone in my bonnet about that at all. But yeah, this was a bit of a problem. So I wondered, can we create a modular platform to reduce design and burden and cost? Spoiler alert, the answer is yes. Otherwise I wouldn't be here giving the talk. So after all those conversations, I kind of looked at this. Now, I was going to bring a physical device with me because I do have them ready to be soldered. However, because of my various injuries the last 6 weeks, I was on crutches over Christmas and the New Year. I then tried to drive somewhere and got stuck in traffic around Leicester, which is never good. So I tried to bend down towards my soldering kit and then went, and then threw these very small components all over my room. And I thought, maybe I don't do that. That's going to be a very expensive thing. So these are the original 3D images, I'm afraid. They're not the actual physical device images. But that's purely because I'm an old lame man, okay? They will be ready soon. They have to be because somebody's just put in funding for a project that requires 100 of them. So they will be done soon, fear ye not. But this is what it looks like. So because anybody who knows me, I'm really good at naming projects and totally brilliant at graphic design, right? So what this shows is, if you can imagine, I've got a kind of G-Shock watch, yeah? So if you imagine that this USB plug here is, which is really hard to do, is this side of the watch, okay? So it's like that. Happy with that? Yep, so this is the screen. These would be positions towards the top alongside the screen for either buttons, and those are the only buttons I could find in KiCad. They are huge. That's not going to be the actual buttons, okay? Or daylight sensors or whatever else next to the display, because obviously a daylight sensor needs to face up. Yep. So this is the form factor, and then you've got at the bottom, and there's a better diagram on the next page. You've got these 2 boards at the bottom, and that board and a board in there at the top, okay? So it's up to 4 boards. Now, you might be thinking, that's probably going to be huge, Adam. That's a ridiculous thing to do. the size of this, including a case, is no bigger than this G-Shock. That's what it's aimed at. Because thankfully, lots of people have done research on the acceptable sizes of smartwatches for different people's sizes and different use cases. So I've built that into the design. This is obviously the full-size one, but there are other form factors. This is what it looks like from the side, just to be a bit more obvious. The way this works is there is a standard backplane, which provides power, connectivity, and it's all kind of I2C, I3C based. These blue plugs, which again, because the manufacturer is as good as graphic design as me, it's not actually green, they're actually kind of silvery, or blue, they're silvery. But these are the connectors between these boards. So if you've anybody used a Raspberry Pi compute module? Yeah, excellent, you're my people. That's good news. So you know the little thin connectors underneath those that have got like 120 pins? It's like that, but there's 6. Okay, so tiny, tiny little thing. So that's what they are. Also use the same connector, but in a different pin layout, and hence a different orientation with lots of text around it to tell you that that's not where it's meant to be plugged in, for things like debugging as well. So this is not just a plug it in and pray. You can do full debugging on these boards as well. Yep. The reason there's a thing sticking out the bottom of this one is because that is the skin contact part of the device. Yeah. So the case would come around here and have a very thin sheath there to allow that to either physically contact or to visually, light contact with the skin. Again, the button isn't going to be that size. That was just the only button I could find in KiCad. These are the boards. So this is option A, full size. You could have all of these things and more. So the reason for designing all these things is twofold. One, we needed to replicate what we did in V1 from a functionality perspective. And 2, I wanted to make an e-health makers kit that we could sell as a dev board to people like yourselves who have Raspberry Pis, hence you're my people. Initially, we could then use those funds to go through certification and then create a commercially supportable product using that. Okay, so we effectively could license this to anybody who wanted a wearable thing for healthcare, for homes, for whatever reason. They could license this. Buy these boards, just like you buy a compute module 4. You've got the design around it, but you want to buy that board because it reduces your design costs. So you could buy the boards of these that you wanted from the project. That funds a project. We can then fund not just the Herald project, but other open healthcare projects, and that's what we're looking at doing, more on that later. But these boards, very quickly, this is the standard connector, this one, with the 2 connection points, top and 2 bottom. So you can have 4 boards on it. With these boards. This is the fan-style chip. This is a flash module, so this is the compute board. So imagine this one being kind of on the top, facing the other way around. That manages the kind of comms between these systems. This is literally just a fairly dumb connector. The only smart bit of this is there's an FTDI built in, so if you do need to do any data transfer, you can have that offloaded, which is quite interesting. The board below it, because the main person I was helping at Oxford with this, there's a student literally in the next research group to us that we have a chat to quite often because we're there. Like, are you a student? I'm like, I honestly am a student. I've just had a hard life. Yeah, I'm a late bloomer. What can I say? So that's why I always wear student clothing when I'm at Oxford, so I don't get asked directions by new students. But yeah, so what he was doing is his team, he bought, I think it was 200 kind of devices that were quite blocky that did GPS tracking. He was looking at water usage in Africa. Sent them out for a year, got them back, tried to get the data off them. 1/3 of them had water ingress, and he couldn't recover it off because it was all proprietary hardware. So he contacted the vendor, they couldn't do it. So I got my soldering iron out and tried all sorts of things for like a year, and we couldn't make it work. And I was like, well, there's definitely a better way of doing this. So this module here, to cut a very long story short, that's the GPS. It's not just stop pressing things. It's not just GPS. I've also thought, well, if you're doing GPS positioning, you'll probably want a gyroscope. You probably want a magnetometer. So that is effectively a positioning board. The board on the right here this is what I call the feedback board, because again, as people at Pivotal will know, I'm terrible at naming things. All right, so this has a ZIF connector for a display. So this would be on the bottom, if you imagine this, plugging that way into the bottom, the ZIF connector would come out and around to the front display. Yeah. It also has its own microprocessor, which is Arduino compatible, because I like my Arduino. So you can actually offload graphics. It's got its own flash there. It's got its own haptic device. It's got its own audio out, its own SPI debug and FTDI, so you can program that on its own and just use that on its own if you want. So the idea here being that you can completely offload. So if somebody just wanted to come in and have a different UI, a different way of interacting with the user, they could just mess around with that board and program that, and the main board would work exactly the same. This one is upside down. So this is the one that actually touches the skin. So that would go on the underneath of the compute module. So this is the 4-board one. There's a button board, 2 blank ones there, and the other one is, ouch, the other one is a daylight sensor board. Okay. So that is the option for full size. You can plug your own in. It's a very straightforward standard to do that. It's just I2C. Right? Or I3C if you've got the right chip. Option B, half size. And the reason I've not got a mock-up of this is because I very kindly went to a Nordic Semiconductor event. So thank you to Nordic Semiconductor if anybody's watching this as a recording later on. The problem I had with this connector, the reason it's so long, is because getting power off of USB and managing a battery and doing all that kind of stuff is quite involved. It requires more than one chip. Apart from, Nordic Semiconductor also got very hacked off with this problem. So they created their own power module, the NPM 1300, which is fantastic. And in one chip, can do all of those things. So what I've actually done now is the half size option. This will be half the size with one of these connectors here. So it'll be thinner. So for people who like kind of Garmin devices to go running with and want something a bit lighter, you can actually do that. So you'll have the option of 2 boards, one top, one bottom. And then you can design that however you wanted. So there would be no screen, you'd sacrifice another board, you'd still have compute and probably something. Either you'd have a GPS, if you like your Strava, or you'd do biomonitoring if you're more interested in fitness, or design your own board that did a bit of both if you really wanted to do that. Yeah. The other interesting thing about this size is once you get down to this size, if you change that USB connector, which is waterproof, by the way, waterproof and dustproof, then you can do some other interesting things with it, because it's not just wearables that you can do. So if you wanted, in a healthcare environment, does anybody want to, and Terence might know this answer, so quiet. Anybody want to guess NHS England? You know syringe pushers that are on carts and they move to the person who needs them? And there's different syringe pushers for different needs and speeds and stuff. And if you get the wrong one, somebody dies. So it's quite important to get the right one. Those syringe pushers and things generally that are mobile within a hospital, does anybody want to hazard a guess how much NHS England buy more than they actually need? 50%. NHS England buys 50% more of these devices than they need for 2 reasons. One, they can't find them, because a nurse, having walked around all the wards to find one for their patient, thinks, I'm going to be clever. I'm going to put that in our side room, and then I know it's there for the next time. But then, of course, she goes home. So nobody else can find it, right? So you could put a tag on those, have a Bluetooth mesh within the hospital, and trace equipment, okay? The other big problem is when a maintenance crew turns up to do a 6-monthly routine check on these things, they really can't find them, which means when it gets wheeled in front of a patient, they look at the date, and it's out of date, they can't use it. So that's why there's 50% more. So the idea here being, you could have tags and then a Bluetooth mesh around a hospital that just tracks that equipment, and you could find it very, very quickly. There's other use cases for that I'll mention later. So that's the beacon use case. The USB use case is if you wanted that mesh to talk to a computer system, hopefully with Kubernetes on it, because we like our Kubernetes, then you'd need some way to go from Bluetooth to RabbitMQ or whatever, right? So the idea with that being a different USB plug on it, so you can plug straight into a computer. And then that will be your modem into the mesh. So that's hence that design. So you can go, and then the other option we've done with these beacons is I've just been testing out a long-range beacon. So anybody heard of Bluetooth long range or the alternative, the other PHY? So Anybody want to hazard, you know Bluetooth, you can barely get a connection over for 10 meters, right? Anybody want to hazard a guess what I've got a point-to-point Bluetooth long-range device this size doing? 11? Guess lower. This is more impressive if you guess very low. So normally Bluetooth in free air will go like 120 meters if you're lucky, right? 4.83 kilometers we've got point-to-point. We're developing a mesh protocol because weirdly, Bluetooth mesh is only supported on the normal PHY, not on the coded PHY, which is a long-range one. So you can't actually run Bluetooth mesh over long range. So I'm coming up with an alternative way of doing that. So solar farms, monitoring water companies who like to put effluent in our rivers, for anybody in England, or those environmental monitoring use cases, you can now do by putting a mesh of these out. So that's the idea behind that one. But again, same form factor, just a slightly different chip, slightly different antenna. The secret sauce of this whole thing is the backplane. It's this backplane here. And all that is, and the connectors aren't shown on this one because it's an old image, but there's a connector there, and on the bottom. So this just handles kind of all the gubbins that you don't want everybody to have to design into their board. So it provides the interconnects for data. It provides voltage at a couple of different voltages. It also provides communication outward, if you want to do that as well. The reason I've done I2C, I2C, however we're pronouncing it today, depending on who you talk to, and I3C is because a lot of devices now do both I2C and SPI. So if you want high-speed, high-amount data, you do SPI. I3C has kind of blurred that a bit. So I'm making sure that this backplane, although for its local stuff, they are I2C devices to say, hey, this is how much power you've got in the battery. Actually, this will work if you have got a compute module like the NRF54H20, which is coming out imminently, or is already out for designers. You can actually do I3C as well. So that enables you to do high-speed data transfer. So you could theoretically stream audio from from the device to whatever. So that's what we're looking at doing as well. Other design points. The OS we're targeting for the stuff we're doing around healthcare is Zephyr. That's what we've been using for the last 3 years. That's Apache T licensed hardware. We started on NRF 5.2 series, 5.3 series, and 5.4 series. But what I'm super, super excited about is the 5.4H20, because that, with its certification, enables you to do some very clever things. And it's also got, for the first time, not just ARM cores on the chip, but also RISC-V cores. So that gets very interesting very quickly, and it also has a third of the power usage of the previous NRF54. And when you bear in mind the NRF54 had a third of the power usage as the NRF52 chip we were using, and we could do that for 6 months, it gets very interesting very quickly. So that's why we use the Nordic chips. Plus, they keep giving me free things, and why not? Okay. Our board designs are all CERN Open Hardware License V2 permissive. So you can use them in both open source and commercial designs. So if you needed to build a commercial product to do something like, I don't know, worker safety on the railways or something, you could totally do that. That'd be allowable. Design restrictions requirements are very few. I was thinking if I do this, I'm going to turn most of the things off. It's going to have limitations. Really, the only limitations I've come up with is that I've made the compute board be responsible to handle the resistors you have to put on the I2C lines, because I3C doesn't have them. So rather than put it on the connector and then mess up every I3C design, I've put them on the compute board. So if you've got a compute board that supports I3C native, it just works. Because all the other devices on all the other boards are backwards compatible in fast mode. So the fast mode I2C devices can be used with I3C. And I'm aiming at PSA certification. So Zephyr and the Nordic chips, so both the physical and the OS, are already PSA certified, which is a certification for secure wearables. And we want this to be certified as well. Use cases, I already mentioned the eHealth Makers Kit, and that's to support medical researchers, but also for you people who love Raspberry Pis like I do. That'll give you enough of the sensors to start using it and get productive with it, and then if you want to design just the little thing that you want to change, you can do that. Unobtrusive health monitoring for independent livings, old people's homes, both for COVID-19 and infection control reasons, but also to monitor vitals and things like that. A study funding was submitted yesterday in the US to fund 50 to 100 of these devices to be used for that, and a mesh network for data transfer for a medical study. So there's already a medical study being put in for that. That's nothing to do with Oxford. It's a separate project in the States. Hospital mesh network, we've already mentioned tracking equipment and Bluetooth long range as well for things like solar farm, environmental monitoring, farm IoT. The reason I'm interested in Bluetooth long range from a healthcare perspective is, again, going back to my experience with the UN Development Programme during the COVID-19 pandemic. They had a problem with the interlink from a village and local wearables. So by using Bluetooth long range mesh, you can actually get an interlink to like a local health centre for the villages around it. So that's why I was interested in that from a healthcare perspective. But there's lots of other use cases you can probably come up with yourselves. Making your own fitness watch if you really wanted to. You could totally do that as well. Availability, I'm doing small batch testing now. I would have been doing it in December, but I managed to break myself as an old man. So once I become a young man again, everything will be fine. But seriously, the refined wearable should be complete in April. We'll make it available for purchase soon after that. It'll have to be as a dev platform initially because we won't have certain certifications. We'll have to do certain of them like FCC Part 5, I think it is. And then once we've sold those, we're actually creating or looking to create a healthcare-specific open source charitable company in England. And the reason for that is it's a very unique thing that you can only really do in England. In that if you create a company with a charitable purpose, you can bid for commercial contracts, but also get donations and get the government to pay you money into that and also go for Innovate UK funds. So that's what I'm doing. The reason I'm doing that is because, and cut a long story short, is Linux Foundation Public Health imploded because we couldn't make it sustainable from a financial perspective, okay? And the problem with that was it was one vertical, it was one industry. And a lot of things we do in healthcare are pretty unique to healthcare. So what I'm doing here is I'm going to form that company initially to fund the Herald project, but we're going to keep some money aside to fund other healthcare open source projects and fund the developers directly and employ them. So that's what I want to do with this. I want to make healthcare sustainable for open source. So that's where the funds are going to be going. I am looking for more people to help out with that, so let me know if you're interested in helping out with that. Getting involved. So we are looking for, always helps, hardware design and testing. Again, I'm a recovering software engineer. My hardware designer, Mishka, I'm not going to mention his last name because he's currently he is Ukrainian. He's currently doing interesting things over there. Obviously, a bit sidetracked at the moment. That's why you've had to put up with my graphics today, not his fantastic graphics. So we are looking for extra help with hardware design, Herald layer, additional software dev, so we can create this kind of secure enclave for medical and fitness data so that you can't breach it. And assistance with PSA certification, documentation, and website, because I'm terrible at graphics. But we're also looking for funding as well. I do need one more charity trustee. I've got most selected. I would like somebody with medical experience. So if anybody knows anyone, let me know. And that's the last thing that's stopping us getting going other than me being broken. And that is the end of my talk. I think I've hit about the right time, maybe a bit shorter than anticipated, actually. So if anybody has any questions, just wait for the microphone.
So I just wanted to say, fantastic talk. I've worked now for 2 little startups that seriously could have used something like this.
Yeah.
The second thing that I want to mention is, have you heard of 802.11ah or Wi-Fi Halo?
Yes.
Oh, okay. All right. Have you looked at that for mesh stuff instead of, why did you decide on Bluetooth?
Yeah. Well, we started with Bluetooth because we already had it. And the Nordic chips do it natively. The interesting thing about Nordic chips is they don't just do Bluetooth. So if you look at what's coming down the pike now, you've got Matter as a standard. And you've got, I always forget the name of these, ultra-wideband radio as well, which is quite interesting, especially for positioning or relative positioning. And then, of course, you've got Bluetooth long range, LoRa, and all these things. So there's nothing in the Herald layer which is tied to Bluetooth. We just have an default implementation, reference implementations Bluetooth. So I have absolutely no problem, and in fact I am already looking at putting a UWB board on there because there's a UK-based wearable company that's just got a large amount of funding some people that we worked with on the COVID-19 project, actually. And they've got a large amount of funding after doing 2 studies in UK hospitals. And they have both Bluetooth and UWB. But they don't have the mesh backbone in the hospitals. So that's where we're looking to help out. So yeah, that's a great question. But yeah, more than happy. If anybody knows any other projects that'd be interested, let me know. I'm getting emails kind of once a month at the moment from different people. It's kind of interesting.